When you support your local PBS station, you help make programs like this one possible.
The greatest triumph of civilization is often seen as our mastery of heat. Yet our conquest of cold is an equally epic journey, from dark beginnings to an ultra-cool frontier. For centuries, cold remained a perplexing mystery, with no obvious practical benefits. Yet in the last 100 years, cold has transformed the way we live and work. Imagine supermarkets without refrigeration, skyscrapers without air conditioning, hospitals without MRI machines and liquid oxygen. We take for granted the technology of coal, yet it has enabled us to explore outer space and the inner depths of our brain. And as we develop new ultra-cold technology to create quantum computers and high-speed networks, it will change the way we work and interact. How did we harness something once considered too fearsome to even investigate? How have scientists and dreamers over the past 4 centuries plunged lower and lower down the temperature scale to conquer the cold and reach its ultimate limit, a holy grail as elusive as the speed limit of light? Absolute Zero. Up next on Nova. Extreme cold has always held a special place in our imagination. For thousands of years, it seemed like a malevolent force associated with death and darkness. Cold was an unexplained phenomenon. Was it a substance, a process, or some special state of being? Back in the 17th century, no one knew, but they certainly felt its effects in the freezing London winters.
17th century England was in the middle of what's now called the Little Ice Age. It was fantastically cold by modern standards. You have to imagine a world lit by fire in which most people are cold most of the time. Cold would have felt like a real presence, a kind of positive agent that was affecting how people felt.
Back then, people felt at the mercy of cold. This was a time when such natural forces were viewed with awe as acts of God. So anyone attempting to tamper with cold did so at his peril. The first to try was an alchemist, Cornelius Drebbel. On a hot summer's day in 1620, King James I and his entourage arrived to experience an unearthly event. Drebbel, who was also the court magician, had a wager with the king that he could turn summer into winter. He would attempt to chill the air in the largest interior space in the British Isles, the Great Hall of Westminster. Drebbel hoped to shake the king to his core.
He had a phenomenally fertile mind. He was an inventor par excellence. His whole world was steeped in a world of alchemy, of perpetual motion machines, of the idea of time, space, planets, moon, sun, gods. He was a fervently religious man. He was a person for whom nature presented a galaxy of possibilities.
Dr. Andrew Shidlow, a chemist with a lifelong fascination for Drebbel, enjoys his reincarnation as the great court magician. Like most alchemists, Drebbel kept his method secret. Dr. Shidlow wants to test his ideas on how Drebbel created artificial cold.
When Drebbel was trying to achieve the lowest temperature possible. He knew that ice, of course, was the freezing point, the coldest you could get normally. But he would have been aware of the fact, through his experience, that mixing ice with different salts could get you a colder temperature.
Salt will lower the temperature at which ice melts. Dr. Shidlow thinks Drebbel probably used common table salt, which gives the biggest temperature drop. But salt and ice alone would not be enough to cool the air within such a large interior. Drebbel was famous for designing elaborate contraptions, a passion shared by Dr. Shidlow, who has an idea for the alchemist's machine.
So here we would have had a fan which would have been turned over, blowing warm air over the cold vessels there, and as the air blows over these cold jars, we would have had, in effect, the world's first air conditioning unit.
But could this really turn summer into winter?
The idea is to stir it in as well as possible in the 5 seconds that you have to do it.
Dr. Shidlow stacks the jars of freezing mixture to create cold corridors for the air to pass through.
You can feel it's very cold. In fact, I could feel cold air actually falling on my hands, because cold air, of course, is denser than warm air, and one can feel it quite clearly on the fingers.
The vital question: would the gust of warm air become cold?
Wolf, I can feel certainly a blast of cold air hitting me as that second cover was released. Well, temperature, we're on 14 at the moment. Yes, keep it going. That's definitely the right direction.
King James would have been shaken by his encounter with man-made cold. Had Drebbel written up his great stunt, he might have gone down in history as the inventor of air conditioning. Yet it would be almost 3 centuries before this idea would actually take off. To advance knowledge and conquer the cold required a very different approach: the scientific method. The fundamental question, what is cold, haunted Robert Boyle nearly 50 years later. The son of the Earl of Cork, a wealthy nobleman, Boyle used his fortune to build an extensive laboratory. Boyle is famous for his experiments on the nature of air, but he also became the first master of cold. Believing it to be an important but neglected subject, he carried out hundreds of experiments.
He worked through, very systematically, a series of ideas about what cold is. Does it come from the air? Does it come from the absence of light? Is it that there are strange, so-called frigorific, cold-making particles?
In Boyle's day, the dominant view was that cold is a primordial substance that bodies take in as they get colder and expel as they warm up. It was this view that Boyle would eventually overturn by a set of carefully devised experiments on water. First, he carefully weighed a barrel of water and took it outside in the snow, leaving it to freeze overnight. Boyle was curious about the way water expanded when it turned to ice. He reasoned that if once the water turned to ice, the barrel weighed more, then perhaps cold was a substance after all. But when they re-weighed the barrel, they discovered it weighed exactly the same.
So what must be happening, Boyle guessed, was that the particles of water were moving further apart. And that was the expansion, not some substance flowing into the barrel from outside.
Boyle was becoming increasingly convinced that cold was not a substance, but something that was happening to individual particles, and he began to think back to his earlier experiments with air. As matter like air becomes warmer, it tends to expand. Boyle imagined the air particles were like tiny springs, gradually unwinding and taking up more space as they heat up.
Boyle's conclusion here was that heat is a form of motion of a particular kind, and that as bodies cool down, they move less and less.
Boyle's longest published book was on the cold. Yet he found its study troublesome and full of hardships, declaring that he felt like a physician trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glass blowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Like the air in Boyle's experiment, heat makes most substances expand. Early thermometers used alcohol, which is lighter than mercury and expands much more with heat. So these Florentine thermometers were sometimes several meters long and often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally accepted temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
The challenge was to find events in nature that always occur at the same temperature and make them fixed points. At the lower end of the scale, that might be ice, just as it begins to melt. At the upper end, it could be wax, heated to its melting point. The first temperature scale to be widely adopted was devised by Gabriel Daniel Fahrenheit, a gifted instrument maker who made thermometers for scientists and physicians across Europe. He had several fixed points. He used a mixture of ice, water, and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small, and that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale between 2 fixed points into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
The story begins with the French physicist Guillaume Amonton.
It's pressure.
He was doing experiments, heating and cooling bodies of air to see how they expand and contract.
Amonton heated air in a glass bulb by placing it in hot water. Just like a hot air balloon, the air in the glass bulb expanded as the increased pressure forced a column of mercury up the tube. Then he tried cooling the air.
He was noticing that, well, when you cool a body of air, the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting this falling temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure. And this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people had actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow, maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point, now known to be minus 273 degrees centigrade. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, most scientists defined cold simply as the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion, and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements.
Indeed, for Lavoisier, it's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
But there was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colorful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works. And it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a chemist meant that few dared challenge his ideas. But this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually lost his head.
Once he was guillotined, his wife left France and eventually met Rumford when he moved to Western Europe in the early 1800s. Rumford then married her, so he'd married the widow of the man who'd founded the theory that he'd destroyed.
The marriage was short-lived. After a tormented year, Rumford left Madame Lavoisier and devoted the rest of his life to his first love, science. It would be nearly 50 years before Rumford's idea that temperature is simply a measure of the movement of particles was accepted. With heat, the particles, what we now know as atoms, speed up, and with cold, they slow down. Rumford's dedication to science led him to become a founder of the Royal Institution in London, and it was here that the next major breakthrough in the conquest of cold would occur. Michael Faraday, who later became famous for his work on electricity and magnetism, would take a critical early step in the long descent towards absolute zero when he was asked to investigate the properties of chlorine using crystals of chlorine hydrate. This experiment was potentially explosive, which is perhaps why it was left to Faraday, and perhaps also why Dr. Andrew Shidlow is curious to repeat it today.
We are about to undertake an exceedingly dangerous experiment in which Michael Faraday in 1823 heated this substance here, the hydrate of chlorine, in a sealed tube. Is that sealed?
That's sealed, Andrew.
That's absolutely brilliant.
In the original experiment, Faraday took the sealed tube and heated the end containing the chlorine hydrate in hot water. He put the other end in an ice bath. Soon he noticed yellow chlorine gas being given off.
Because the gas is being produced, pressure's building up. Ray, this is where it starts to get dangerous. So if you now take a few steps back.
When Faraday did the experiment, a visitor, Dr. Paris, came by to see what he was up to. Paris pointed out some oily matter in the bottom of the tube. Faraday was curious and decided to break open the tube.
Right, so let's have a look inside here.
The explosion sent shards of glass flying. With the sudden release of pressure, the oily liquid vanished.
And there we are.
Is that what happened?
Yeah, that's exactly what happened. It popped open, glass flew. And can you detect the strong smell of chlorine?
I can now.
Absolutely. Well, he detected the strong smell of chlorine, and this was a major mystery for him.
Faraday soon realized the increased pressure inside the sealed tube had caused the gas to liquefy. And when the tube was broken, the oily liquid evaporated. Just as heat must be applied to evaporate water, he saw that energy from the surrounding air had transformed liquid chlorine into a gas. In a brilliant deduction, Faraday realized that by absorbing heat from the air, he had cooled or refrigerated the surroundings. Michael Faraday had produced cold. Later, he used the same technique with ammonia, which absorbs even more heat. He predicted that one day this cooling might be commercially useful. Faraday took no interest in commercial exploitation. But across the Atlantic, a Yankee entrepreneur had a very different philosophy. Frederick Tudor had a chance conversation with his brother that led him on a path to become one of the richest men in America.
The story goes at the dinner table, they were trying to decide what they had on their father's farm they could make money off of, and certainly there was a lot of rocks, but people weren't going to pay for that. So they came up with the idea of maybe ice, because some areas did not have ice. And it seemed kind of crazy at first, but it paid off.
When Tudor began harvesting ice from New England ponds, he soon realized he needed specialized tools to keep up with the huge demand.
We had the saws, and the saws were improvement over the old wood saws. They have teeth that are sharpened on both sides and set, so it cuts on both the up and the down stroke. And a crew could clear a 3-acre pond easily in a couple of days.
Tudor's dream to make ice available to all was not confined to New England. He wanted to ship ice to hot parts of the world, like the Caribbean and the Deep South.
When Tudor first tried to convince shipmasters to put his load of frozen water into the ships, they all refused because they told him that water belonged outside the hull, not inside. So he had to go find other investors to get the money to buy his own ship, and he bought a ship by the name of the Favorite.
New England became the refrigerator for the world, with ice shipments to the Caribbean, the coast of South America and Europe. Tudor even reached India and China. Watching the ice cutters working Walden Pond, Henry Thoreau marveled that water from his bathing beach was traveling halfway round the globe to end up in the cup of an East Indian philosopher. Tudor, who soon became known as the Ice King, began using horses and huge teams of workers to harvest larger and larger lakes as the demand for ice grew. During the latter half of the 19th century, the ice industry eventually employed tens of thousands of people.
Tudor became the largest distributor of ice, and he became one of the first American millionaires. And we're talking about one of his ships going to the Caribbean, giving him a profit of $6,000. Now, this is in a time period when people were earning $200 to $300 a year, the average family. So someone earning thousands of dollars was just inconceivable. And that would be losing 20% of your ice when it got there. There was still huge amounts of profit.
Tudor's success was based on an extraordinary physical property of ice. It takes the same amount of heat to melt a block of ice as it does to heat an equivalent quantity of water to around 80 degrees Celsius. This meant that ice took a long time to melt, even when shipped to hotter climates. What started out as a small family enterprise turned into a global business. Frederick Tudor had industrialized coal in the same way the great pioneers of steam had harnessed heat. By the 1830s, the Industrial Revolution was in full swing. Yet ironically, it was not until a small group of scientists worked out the underlying principles of how steam engines convert heat into motion that the next step in the conquest of coal could be made. Only after solving this riddle of heat engines could the first cold engines be made to produce artificial refrigeration.
How much useful work can you get out of a given amount of heat? By the early 1800s, that had become the single most important economic problem in Europe. To make a profit was to convert heat into motion efficiently, without wasting heat and getting the maximum amount of mechanical effect.
The first person to really engage with this problem was a young French artillery engineer, Sadi Carnot. He thought that improving the efficiency of steam engines might help France's flagging economy after defeat at Waterloo in 1815. Working at the Conservatoire des Arts et Métiers, he began to analyze how a steam engine was able to turn heat into mechanical work.
In steam engines, it looks as though heat is flowing around the engine, and as it flows, the engine does mechanical work. The implication there is that heat is neither consumed nor destroyed. You simply circulate it around and it does work.
Carnot likened this flow of heat to the flow of water over a water wheel. He saw that the amount of mechanical work produced depended on how far the water fell. His novel idea was that steam engines worked in a similar way, except this fall was a fall in temperature from the hottest to the coldest part of the engine. The greater the temperature difference, the more work was produced. Carnot distilled these profound ideas into an accessible book for general readers, which meant it was largely ignored by scientists instead of being heralded as a classic.
Well, this is the book. It's Carnot's only publication, Reflections on the Motive Power of Fire of 1824. a small book, 118 pages only, published just 600 copies, and in his own lifetime it's virtually unknown. 20 years after the publication, William Thomson, the Scottish physicist, is absolutely intent on finding a copy. He's here in Paris, and the accounts we have suggest that he spends a great deal of time visiting bookshops, visiting the bouquinistes on the banks of the Seine, looking, always asking for the book, and the booksellers tell him they've never even heard of it.
William Thomson, who would later become Lord Kelvin, a giant in this new field of thermodynamics, was impressed by Carnot's idea that the movement of heat produced useful work in the machine. But when he returned home, he heard about an alternative theory from a Manchester brewer called James Joule.
Joule had this notion that Carnot was wrong, that heat wasn't producing work just by its movement. Heat was actually turning into mechanical work, which is a very strange idea when you think about it. We're all now used to thinking about energy and how it can take all different forms. But it was a revolutionary idea that heat and something like mechanical energy were at bottom the same kind of thing.
The experiment that convinced Joule of this was set up in the cellar of his brewery. It converted mechanical movement into heat, almost like a steam engine in reverse. He used falling weights to drive paddles around the drum of water. The friction from this process generated a minute amount of heat. Only brewers had thermometers accurate enough to register this tiny temperature increase caused by a measured amount of mechanical work.
Joule's work mattered because it was the first time that anyone had convincingly measured the exchange rate between movement and heat. He'd proved the existence of something that converts between heat and motion. That something was going to be called energy. And it's for that reason that the basic unit of energy in the new international system of units is named after him, the joule.
Joule and Carnot's ideas were combined by Thomson to produce what would later be known as the laws of thermodynamics. The first law, from Joule's work, states that energy can be converted from one form to another, but can never be created or destroyed. The second law, from Carnot's theory, states that heat flows in one direction only, from hot to cold. In the second half of the 19th century, this new understanding paved the way for steam power to artificially produce ice. Ice-making machines like this one were based on principles discovered by Michael Faraday, who showed when ammonia changes from a liquid to a gas, it absorbs heat from its surroundings. It's part of what is now known as a refrigeration cycle. In the first stage of this cycle, gigantic pistons compress ammonia gas into a hot liquid. The hot liquefied ammonia is pumped into condenser coils, where it's cooled and fed into pipes beneath giant water tanks. Then the pressure is released, and the liquid ammonia evaporates, absorbing heat from the surrounding water. Gradually, the tanks of water become blocks of ice. By the 1880s, many towns across America had ice plants like this one, which could produce 150 tons of ice a day. For the first time, artificially produced ice was threatening the natural ice trade created by Frederick Tudor. America's appetite for ice was insatiable. Slaughterhouses, breweries, and food warehouses all needed ice. Animals were disassembled on production lines in Chicago, and the meat was loaded into ice-cooled boxcars to be shipped by railroad.
Livestock on its way to the great meat packing centers of the nation, to markets everywhere. Food of every sort, safely and quickly delivered in refrigerator cars.
As fruit and vegetables became available out of season, urban diets improved, making city dwellers the best-fed people in the world. And to keep everything fresh at home, the Iceman made his weekly delivery to recharge the refrigerator.
Refrigeration makes a tremendous difference in people's lives. First of all, in the diet, what is possible for them to eat. They can go to the store once a week. They don't have to go every day. They can obtain at that store foods that are from almost anywhere in the world that have been transported and kept cool, and then they can keep them in their own home.
Eventually, the Iceman disappeared as more and more households bought electric refrigerators. These used the same basic principles as the old ice-making machines. Liquid ammonia circulating in pipes evaporates, draining the heat away from the food inside. Compressed by an electric pump, the gas is condensed back into liquid ammonia, and the cycle begins again.
The electric power companies loved refrigerators because they ran all day and all night. They may not have used that much power for each hour, but they continued to use that. So one of the ways that they sold rural electrification was the possibility of having your own refrigerator.
In the early days, the freezer was used to freeze water, nothing else. Freezing was seen as having the same damaging effects as frost. The man who would change this idea forever was a scientist and explorer named Clarence Birdseye. In 1912, Birdseye set off on an expedition to Labrador, and the temperature dropped to 40 degrees below freezing. The Inuit had taught Birdseye how to ice fish by cutting a hole in the ice several feet thick. When he caught a fish, he found it froze almost as soon as it hit the air. This process seemed to preserve the fish in a unique way.
When you went to cook this fish, it tasted just as good as it's fresh. And he couldn't figure that out because when he froze fish at home, they would taste terrible. So when he got back home, he finally tried to figure out what was the difference between this quick freezing and the usual freezing.
Under closer examination, he could see what was happening to the fish cells. With slow freezing, large ice crystals formed, which distorted and ruptured the cells. When thawed, the tissue collapsed and all the nutrients and flavor washed away. The so-called mushy strawberry syndrome. But with fast freezing, only tiny ice crystals were formed inside the cells, and these caused little damage. It was all down to the speed of the freezing process. A simple concept, but it took Clarence Birdseye another 10 years to perfect a commercial fast freezing technique that would mimic the natural process he'd experienced in Labrador. In 1924, he opened a flash freezing plant in Gloucester, Massachusetts, that froze freshly landed fish at minus 45 degrees.
He then extended that to all sorts of other kinds of meats and produce and vegetables, and almost single-handedly invented the frozen food industry.
Refrigerators and freezers would eventually become icons of modern living. But there was a less visible cold transformation happening at the same time. This would also have a huge impact on urban life: the cooling of the air itself. 3 centuries had passed since Cornelius Drebbel had shaken King James in Westminster. Now, at the dawn of the 20th century, air cooling was about to shake the world.
Tell me, what is the lowdown on this air conditioning thing?
Now you've started something by asking me that.
Air conditioning was about to transform modern life, and the person largely responsible was Willis Carrier, who started off working for a company that made fans.
Carrier is sent to Brooklyn for a very special job in 1902. The company that publishes the magazine Judge, one of the most popular full-color magazines in America at this particular time, is having a huge problem. It's July in Brooklyn, and the ink for which they use on their beautiful covers is sliding off the pages. It will not stick because the humidity is too high. Carrier, using some principles that he's been developing as a young new employee of this fan company, finds a way to get out the July 1902 run of the Judge magazine, and from there he begins to eventually build his air conditioning empire.
It's based on a simple principle.
Control of humidity through control of temperature. That was Willis Carrier's idea.
He used refrigeration to cool the water vapor in the humid air. The vapor condensed into droplets, leaving the air dry and cool. The demand for air conditioning gradually grew. In the 1920s, movie houses were among the first to promote the benefits. People would flock there in summer to escape the heat.
The movies are wildly popular. And the air conditioning certainly helps to attract an audience, especially if they happen to be walking down the street on a horribly hot day and they duck into this movie theater and have this wonderful experience.
Air conditioning became increasingly common in the workplace, too, particularly in the South, where textile and tobacco factories were almost unbearable without cooling.
When employees breathe good air and feel comfortable, they work faster and do a better job.
I think some people think that these were nice, compassionate employers who were cooling down the workplace for the workers, but of course nothing could be further from the truth. That was an inadvertent byproduct, but actually this was a quality control device to control the breaking of fibers in cotton mills, to get consistent quality control in these various industries, to control the dust that had bedeviled tobacco stemming room workers for decades. I think the workers obviously went home and to their unair-conditioned shacks in most cases, and talked about how nice and cool it was working during the day.
It's silly to suffer from the heat when you can afford the modest cost of air conditioning.
By the 1950s, people were air conditioning their homes with standalone window units that could be easily installed. This wasn't just an appliance. It offered a new, cool way of life.
Walking down a typical southern street prior to the air conditioning revolution, you would have seen families, individuals outside. They would have been on their porches, on each other's porches. There was a visiting tradition, a real sense of community. Well, I think all that changes with air conditioning. You walk down that same street, and basically what you'll hear are not the voices of people talking on the porch, you'll hear the whir of the compressors.
Guess what we've got? An RCA room air conditioner. I'm a woman, and I know how much pure air means to Mother in keeping our rooms clean and free from dust and dirt.
control of the cold has transformed city life. Refrigeration helped cities expand outwards by enabling large numbers of people to live at great distances from their source of food. Air conditioning enabled cities to expand upwards. Beyond 20 stories, high winds make open windows impractical. But with air conditioning, 100-story skyscrapers were possible.
Technologies emerge which not only worked to insulate human society against the evils of cold, but turned cold into a productive, manageable, effective resource. On the one hand, the steam engine, on the other, the refrigerator. Those two great symbols of 19th century world, which completely changed the society and economy of the planet. All that is part of, I think, what we could call bringing cold to market, turning it from an evil agent that you feared into a force of nature from which you could profit.
The explosive growth of the modern world over the last 2 centuries owes much to the conquest of cold. But this was only the beginning of the journey down the temperature scale. Going lower would be even harder, but would produce greater wonders that promise extraordinary innovations for the future. With rival scientists racing toward the final frontier, the pace quickens and the molecular dance slows as they approach the holy grail of cold, absolute zero. A century ago, Antarctic explorers were pushing further and further towards the coldest place on Earth, the South Pole, where temperatures can plummet to minus 80 degrees. The competition to reach this goal was matched by a less publicized but equally daunting scientific endeavor, the attempt to reach the coldest point in the universe, absolute zero. Was it possible to attain this ultimate limit of temperature, minus 273 degrees Celsius? Only in a laboratory, by liquefying gases, could scientific adventurers take the first steps towards this holy grail, a place where atoms come to a virtual standstill, utterly drained of all thermal energy. Among the front runners in the race towards absolute zero was James Dewar, a professor at the Royal Institution in London.
It will be the greatest achievement of our age.
In 1891, he gave one of his celebrated Friday night public lectures on the wonders of the super cold to celebrate the centenary of his great predecessor, Michael Faraday.
The descent to a temperature within 5 degrees of zero would open up new vistas of scientific inquiry, which would add immensely to our knowledge of the properties of matter.
James Dewar is a canny and I think very ambitious, practically minded Scottish scientist. He could really show both his colleagues and the fee-paying audiences some of the secrets of nature.
Take this rubber ball. It bounces well, I think you'll agree. But let's see what happens after a few seconds immersion in liquid oxygen.
Dewar invented a thermal insulated container to carry out his research. And scientists to this day still call it a Dewar flask.
Now, let's see what happens.
This phantasmagoric aspect of science always helped science to be accepted by the public. Though it is a little mystifying, it did play a role of having society, having the public accept that these weird people in the laboratories are doing truly interesting, if not magical things.
Dewar's dream was to take on the mantle of the Royal Institution's greatest scientist, Michael Faraday. "70 years earlier, Faraday had done experiments showing that under pressure, gases like chlorine and ammonia liquefy. He was curious to see if this method of pressurizing gases into liquids could be used for all gases. But some, what he called the permanent gases, oxygen, nitrogen, hydrogen, would not liquefy, no matter how much pressure he applied. So he abandoned this line of research.
Faraday's was a mind full of subtle powers, of divination into nature's secrets. And although unable to liquefy the permanent gases, he expressed faith in the potentialities of experimental inquiry. The lowest point of temperature attained by Faraday was minus 130 degrees centigrade.
It was not until 1873 that a Dutch theoretical physicist, van der Waals, finally explained why these gases were not liquefying. By estimating the size of molecules and the forces between them, he showed that to liquefy these gases using pressure, they each had to be cooled below a critical temperature. At last he had shown the way to liquefy the so-called permanent gases was to cool them. Oxygen was first, and then nitrogen, reaching a new low temperature of almost minus 200 degrees centigrade.
Only the last of the permanent gases remains to be liquefied. Hydrogen, in the vicinity of minus 250 degrees centigrade. It will be the greatest achievement of our age, a triumph of science.
Dewar was determined to be the first to ascend what he called Mount Hydrogen, but he was not alone. The competitor Dewar feared most was a brilliant Dutchman, Heike Kamerlingh Onnes.
Kamerlingh Onnes was younger than Dewar, and to a certain extent looked up to the Scotsman as his senior. Dewar didn't have the same, if you'll pardon the expression, warm feelings towards his rival in the race for cold.
Dewar recognized that Kamerlingh Onnes had a new radical approach to science and was planning an industrial-scale lab.
When Onnes took over the physics laboratory in Leiden, he was only 29 years old. And, well, he gave his inaugural address here in this lecture room, the big lecture room of the Academy building of Leiden University, and it was all there. He was explaining what to do in the next years, and he was talking about liquefying gases, making Dutch physics famous abroad, and, well, it was amazing how far-sighted all those visions were.
Kamerlingh Onnes's lab was more like a factory. He recruited instrument makers, glassblowers, and a cadre of young assistants who became known as Blue Boys because of their blue lab coats. Later, he set up a technical training school, which still exists to this day. Dewar and Onnes could not have been more different. Dewar was very secretive about his work, hiding crucial parts of apparatus from public view before his lectures. Onnes, on the other hand, openly shared his lab's steady progress in a monthly journal. Onnes was the tortoise to Dewar's hare.
In the case of Dewar, you had a brilliant experimenter, a person who could actually build the instruments himself, and a person who really believed in the brute force approach, and that is, have your instruments, set up your experiment, and try as hard as you can, and then you'll get the results you want to get. In the case of Camelones, you have a totally different approach. He is the beginning of what later on was known as big science.
Unlike Dewar, Onnes thought detailed calculations based on theory were vital before embarking on experiments. He was a disciple and close friend of van der Waals, whose theory had helped solve the problem of liquefying permanent gases. Though their approaches were different, Kamerlingh Onnes and Dewar used a similar process in their attempts to liquefy hydrogen. Their idea was to go step by step down a cascade, using a series of different gases that liquefy at lower and lower temperatures. By applying pressure on the first gas and releasing it into a cooling coil submerged in a coolant, it liquefies. When this liquefied gas enters the next vessel, it becomes the coolant for the second gas in the chain. When the next gas is pressurized and passes through the inner coil, it liquefies and is at an even lower temperature. The second liquid goes on to cool the next gas, and so on. Step by step, the liquefied gases become colder and colder. Each one is used to lower the temperature of the next gas sufficiently for it to liquefy. In the final stage, where hydrogen gas is cooled, the idea was to put it under enormous pressure, 180 times atmospheric pressure, and then suddenly release it through a valve. This would trigger a massive drop in temperature, sufficient to turn hydrogen gas into liquid hydrogen at minus 252 degrees, just 21 degrees above absolute zero.
Here was the risky bit, because his apparatus was going down in temperature, getting very, very cold, so very fragile, quite easy to fracture, while at the same time the pressures he was working at were very, very high, so the possibility of explosion. He took the most amazing risks, both with himself, he was a lion of a man in terms of courage, and with those around him. All the equipment he was working with could have crumbled or blown up, and more than occasionally it did.
Dewar had many explosions in his lab. Several times, assistants lost an eye as shards of glass catapulted through the air.
In the notebook, he actually jots down many details of what happened in the apparatus, but not what happened to his assistants. So somehow you get the impression that apparatus is more important than the assistants.
Over in Leiden, Onnes was facing anxious city officials who were so worried about the risk of explosions that they ordered the lab to be shut down. Dewar wrote a letter of protest on behalf of Onnes. But the Leiden lab remained closed for 2 years.
Well, Onnes had to wait and to wait and to wait. Dewar was already starting with liquefying hydrogen, and well, Onnes had the apparatus to do so too, but it just couldn't start, so we had lost the battle before it was even begun.
The years 1898, Dewar has been working on trying to liquefy hydrogen for more than 20 years, and he's finally ready to make the final assault on Mount Hydrogen.
By using liquid oxygen, they brought down the temperature of the hydrogen gas to minus 200 degrees Celsius. They increased the pressure till the vessels were almost bursting, and then opened the last valve in the cascade.
Shortly after starting, the nozzle plugged, but it got free by good luck. And almost immediately drops of liquid began to fall, and soon accumulated 20 cubic centimeters.
Dewar had liquefied hydrogen, the last of the so-called permanent gases. To prove it, he took a small tube of liquid oxygen and plunged it into the new liquid. Instantly, the liquid oxygen froze solid. Now he was convinced. He had produced the coldest liquid on Earth and had come closer to absolute zero than anyone else.
Dewar thought that he had done the most amazing feat of science in the world, that he would be immediately celebrated for it and get whatever prizes there were available. And that didn't happen.
I think for Dewar, it was the ambition of a mountaineer. You've climbed the highest mountain peak that you can see in the range around you, and just as you get to the top of the peak, there's an even higher mountain just beyond.
That new mountain was helium, a recently discovered inert gas that was originally thought only to exist on the sun. Van der Waals' theory predicted helium would liquefy at an even lower temperature than hydrogen, at around 5 degrees above absolute zero. Now, all Dewar had to do was obtain some. It should not have been difficult. The two chemists who had discovered the inert gases, Lord Rayleigh and William Ramsay, often worked together in the lab next door. Unfortunately, Dewar had made enemies of both of them by refusing to collaborate and belittling their achievements, so they had no desire to share their helium.
Camerlingionis was faced with the same problem as Dewar, which is, where can I get a supply of helium gas? And he actually asked Dewar to try and collaborate with him, too. And Dewar said, I'm having such a problem getting the gas by myself, I can't possibly give you any. I'd like to, but I can't.
Eventually, each found a supply. But Onnes's industrial approach paid dividends. After 3 years, he had amassed enough helium gas to begin experiments. The tortoise was beginning to pull away from the hare. At the same time, Dewar was running out of resources. To make matters worse, a lab assistant turned a knob the wrong way, releasing a whole canister of helium into the air. For 6 months, the lab couldn't do any work.
At one point, Dewar writes to Camerlingionis telling him that he's not in the race anymore. He thinks that the problems for liquefying helium are such that he's not able to complete the job.
The battlefields of science are the centers of a perpetual warfare in which there is no hope of a final victory. To serve in the scientific army, to have shown the initiative, is enough to satisfy the legitimate ambition of every earnest student of nature. Thank you.
In the summer of 1908, Onnes summoned his chief assistant Flim from across the river. They were finally ready to liquefy helium. At 5:45 on the morning of July the 10th, he assembled his team at the lab. They had rehearsed the drill many times before. Leiden was a small university town, and the word quickly spread that this was the big day. It took until lunchtime to make sure the apparatus was purged of the last traces of air. By 3 in the afternoon, work was so intense that when his wife arrived with lunch, he asked her to feed him so he didn't have to stop. At 6:30 in the evening, the temperature began to drop below that of liquid hydrogen. But then, it seemed to stick.
Honest doesn't know why this is. And a colleague comes in and he suggests that that means maybe they've actually succeeded and they don't even know it yet. So Honest takes an electric lamp type thing and he goes underneath the apparatus and looks, and sure enough, there in the vial is this liquid sitting there quietly. It's liquefied helium.
They had reached minus 268 degrees Celsius, just 5 degrees above absolute zero, and finally produced liquid helium. This monumental achievement eventually won Onnes the Nobel Prize. When James Dewar heard that he had lost the race to Kamerlingh Onnes, it reignited a festering resentment. Dewar berated his long-suffering assistant Lennox for failing to provide enough helium. Only this time, Lennox had had enough. He walked out of the Royal Institution, vowing never to return until Dewar was dead. And he kept his word. For Dewar, it was the end of his low-temperature research. James Dewar's dream of reaching absolute zero was over. Although he had won the first race to liquefy hydrogen, it never attracted the same accolades as liquefying helium. He abandoned low-temperature physics and moved on to investigate other phenomena, such as the science of soap bubbles.
I think it's really impressive how often scientists do seem to be driven by the spirit of competition, by the spirit of getting there first. But what's really fascinating about these races, the race for absolute zero, is that the goalposts move as you're playing the game. The race in science is not for a predetermined end, and once you're there, the story's over, the curtain comes down. That's not at all what it's like. Rather, it turns out you find things you didn't expect. Nature is cunning, as Einstein would have said, and she is constantly posing a new challenge, unanticipated by those people who start out on the race.
This is just what happened in Leiden, as Onnes's team began to investigate how materials conduct electricity at very low temperatures. They observed in a sample of mercury that at around 4 degrees above absolute zero, all resistance to the flow of electricity abruptly vanished. Onnes later invented a word to describe this new phenomenon. He called it superconductivity.
We have a circular ring of permanent magnets which are producing a magnetic field. And now when we put a superconducting puck over it and give it a little push, the magnetic field repels the superconductor.
The magnetic field from the track induces a current in the superconducting puck, which in turn creates an opposite magnetic field that makes the puck levitate.
It produces a magnetic field like a North Pole against the North Pole, and that's why you have the repulsion.
As the puck warms up, its superconducting properties vanish, along with its magnetically induced field. For decades after its discovery in 1911, the underlying cause of superconductivity remained a mystery.
Every major physicist, every major theoretical physicist had his own theory of superconductivity. Everybody tried to solve it, but it was unsuccessful.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them. In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Dan Kleppner and his MIT colleague Tom Graytak began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated, we were having a hard time moving forward.
Now others decided to take up the challenge. Two physicists from MIT met in Boulder, Colorado, and came up with a different approach to the problem. Rather than focusing on the lighter atoms of the periodic table, they hit upon the idea of using much heavier metallic atoms, like rubidium and cesium. But would using these giants enable them to reach closer to absolute zero?
The idea in the field in those days was that the light things like hydrogen and lithium would be easier. And there were some good reasons for thinking that, but we had other ideas.
Yeah, sort of gut intuition in some sense.
Their plan was to use a laser beam to cool the atoms, a technique that had already been tried by physicists at MIT. Lasers are usually associated with making things hot, but if they are tuned to the same frequency as atoms traveling at a particular speed, lasers can cool them down. When the stream of light particles from the laser hits the selected atoms in the gas cloud, they slow down and become cold. Laser cooling was a new tool that had the potential to reduce the temperature of a gas to within a few millionths of a degree of absolute zero. But Cornell and Wyman were not the only ones excited by this prospect. A new scientist had arrived at MIT.
It was in late 91 or early 92 that we had an idea how a different arrangement of laser beams would be able to cool atoms to higher density. And it worked. And this was really a trigger point. I will never forget the excitement in those group meetings when we discussed what do we next. Because with higher density, there are many things you can do. Could we now push to Bose-Einstein condensation? You see, well, lots of cables and electronics.
All the resources of Ketterle's lab were redirected to make a condensate in sodium atoms.
And right here, this is an atomic beam oven. What is wrapped in tin foil is a little vacuum chamber where we heat up metallic sodium so the metallic sodium melts and evaporates. And it's ultimately the sodium vapor, the sodium atoms, which we tried to Bose-Einstein condense.
MIT, Boulder, and several other labs were chasing the same goal. It had echoes of the race to produce liquid helium almost a century earlier.
As I tell my students today, anything worth doing is worth doing quickly because science moves on, and we're all mortal, and you want to do things.
While MIT was installing its sophisticated lasers, Carl Wyman's approach was small is beautiful.
In some cases, he was ripping open old fax machines and taking out the little chip inside that made the laser and showed that you could take these lasers and put them into a home-built piece of apparatus, stabilize the laser, and use them to do spectroscopy and laser cooling.
This is actually our first, what's called the vapor cell optical trap. You can see it's kind of this old cruddy thing pulled together glass where we could send laser beams in from all the different directions and have just a little bit of the atoms we wanted to cool.
As well as bombarding the atoms with lasers, they also trapped them in a strong magnetic field.
We would try this sort of magnetic trap, that sort of magnetic trap, this sort of imaging, that sort of imaging, that sort of cooling. All those things we could do without building a whole new chamber each time. We tried literally 4 different magnetic traps in 4 years, instead of having a 3 or 4 year construction project for each one.
By being fast and flexible, the Boulder Group hoped to beat their old lab at MIT. But MIT had its own plans.
There was a sense of competition, but it was what I would call friendly competition. I mean, can you imagine 2 athletes? They are in the same training camps, they help each other, they even give tips to each other. But then, when it comes to the race, everybody wants to be the first.
The rival groups were both using magnetic trapping and lasers to cool their atoms. But for the final push towards absolute zero, to turn these atoms of gas into the quantum state Einstein had predicted, they needed one more cooling technique: evaporative cooling.
It's just like with this coffee. The steam coming off the coffee is the hottest of the coffee molecules escaping and carrying away more than their fair share of energy. In the case of the atoms, we keep the atoms in a sort of magnetic bowl, and we confine the atoms there. They zoom around inside the bowl, and then the hottest ones have enough energy to roll up the side of the bowl and fall over the edge, slop over the edge, taking away with them much more than their fair share of energy, and the atoms that remain have less and less energy, which means they move slower and slower and start to cluster near the bottom. And as that happens, we gradually lower the edges of the magnetic trap, and always, so there's just a few atoms that can escape, until finally the remaining atoms cluster near the bottom of the bowl, huddled together. They get colder and colder and denser, and eventually in this way evaporation forces the Bose-Einstein condensation to occur.
The race to produce a Bose-Einstein condensate was intensifying.
At every major meeting, Eric Cornell and I gave talks or talked to each other. We were keenly aware that we were both working towards the same goal.
In June 1995, the Boulder Group was working round the clock, knowing that MIT and several other labs were also poised to produce the first condensate. An official visit from a government funding agency was the last thing they needed.
We didn't want to close down the lab or clean up our lab or put up posters. We wanted to work very hard, so the senior dignitaries in the 3-piece suits and so on came in to the lab, and we left the lights off, and everyone continued to work, and I made them keep their voices down and talked to them rather in a hurried way, and then sort of shuffled them out the door, and they all had a slightly puzzled look on their face, because it probably had never happened to them before in the history of being a visiting committee, that they were treated with as little pomp. And later I actually met one of the guys who said, I suspected something was up that day, because otherwise you never would have dared to do that.
June the 5th, 1995, turned out to be a big day in the history of physics. The Boulder Group seemed to have made what Einstein had theorized 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here, you know. Let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast, and even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
At a temperature of 170 billionth of a degree above absolute zero, Wyman and Cornell created a pure Bose-Einstein condensate in a gas cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know.
One of the first things you need to understand about Bose-Einstein condensation is how very, very cold it is. Where we live at room temperature is far above absolute zero on this scale. Imagine that room temperature is represented by London, thousands of kilometers from here. Then on that scale, if we imagine right here where I'm standing in Boulder is absolute zero, the coldest possible temperature, then how close are we to absolute zero? If we think of London as being room temperature and right where I am is absolute zero, then Bose-Einstein condensation occurs just the thickness of this pencil lead away from absolute zero.
Within months of the Boulder Group's success, Wolfgang Ketterle produced an even larger condensate from 500,000 sodium atoms, slowed down to a virtual standstill, causing their wave functions to overlap to produce an entirely new state of matter. At last, quantum mechanics was more than just a theoretical construct. It was something that could be seen with the naked eye. Cornell, Ketterle, and Wyman shared the Nobel Prize for Physics in 2001.
One of the things the Nobel Prize means, and the ceremony means, that everybody remembers Eric's the person who forgot to bow to the king.
There was a breakdown of protocol on my part. There was no excuse because they actually drill us. It's more like you have a series of rehearsals practicing how to bow to the king, and I somehow managed to bollocks it up at the last possible moment. And I thought maybe, Carl, who came after me, would do this, make the same mistake, and then no one would figure it out. But no, he was perfect.
I heard about the Nobel Prize when I was woken up by a telephone call, which was at, I think, 5:30 in the morning. So you wake up, you go to the telephone, and somebody tells you, congratulations, you've won the Nobel Prize. You're still tired, your brain is not fully functional, but you realize this is big, and what you feel is pride for MIT, your collaborators, for yourself. It's wonderful to see that your work gets recognized and acknowledged in this way.
Like any great adventure, the pursuit of science offers no guarantee of success. But for the godfather of ultra-cold atoms, persistence eventually paid off. In 1998, after 20 years of struggling to obtain a condensate in hydrogen, Dan Kleppner finally succeeded. For a few fleeting moments, his dream came true.
Of course, we were delighted, and I think everyone was delighted, because we'd been working on it for so long. It's kind of embarrassing to have this group which helped start the work and was working away there fruitlessly while everyone was enjoying success. When we got it, everyone was happy.
To see that an effort which lasted for 20 years, which took so much patience, frustration, and tenacity, to see that succeed is just emotional, it's liberating. I will never forget this standing ovation which Dan Kleppner received at the Varenna Summer School when he announced Bose-Einstein condensation in hydrogen.
Everybody just got up and it was sort of like an opera where everybody just cheered and people were crying, and because everybody realized that they had finished the race, but too late. And it wasn't going to work out, but in some sense they had really stimulated the whole field. So it was a very moving moment.
For the pioneers who had realized Einstein's dream and created condensates, it was the end of an extraordinary decade of physics. Now there was a new challenge, to work out what to do with them. At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, you know, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, you know, to a human level, I thought that was just absolutely fascinating.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium. And since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression. And it'll end up being compressed from 1 to 2 miles down to 0.001 micron, or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to store and even process information. Even now, cold atoms are being turned into prototype quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool. It's fun, and we can do it. Right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great. Yes, look at that.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
A qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of parallel computation, but in a parallel computer, one processor does this, one processor does that. So you have two processors doing this and that. In a quantum computer, you have only one processor that's doing this and that at the same time.
Today, computers are limited in the amount of information they can handle by the heat and number of the circuits. Here, within a giant Dewar flask, lies a prototype quantum computer surrounded by its supercooled, superconducting magnet. In the future, quantum computing could be used to predict incredibly complex quantum interactions, such as how a new drug acts on faulty biochemistry, or to solve complex encryption problems like decoding prime numbers that are the key to internet security. Already, supercooled quantum devices are mapping the magnetic activity of the brain. Often, the promised benefits from a scientific breakthrough take a long time to emerge. Many predicted that by this century, energy-saving superconducting power lines and maglev bullet trains would be crisscrossing the continents. Perhaps as world energy supplies decline, these technologies, once seen as too costly, will start to take off. This weird quantum world is part of a new frontier opened up by the descent towards absolute zero. It's been a remarkable journey for scientists into unknown territories far beyond the narrow confines of Earth. On the Kelvin temperature scale, which begins at absolute zero, the temperature of the Sun is around 5,000 Kelvin. At 1,000 Kelvin, metals melt. At 300, we reach what we think of as room temperature. Air liquefies at 100 Kelvin. Hydrogen at 20. Helium at 4 Kelvin. The deepest outer space is 3 degrees above absolute zero. But the descent doesn't stop there. With ultra-cold refrigerators, the decimal point shifts 3 places to a few 1,000ths of a degree. And laser cooling takes it down 3 more places to a 1,000,000th of a degree, the temperature of a Bose-Einstein condensate. With magnetic cooling, we shift 4 more decimal places until we reach the coldest recorded temperature in the universe, created at a lab in Helsinki, 100 picokelvin, or a 1/10 of a 1,000,000th of a degree above absolute zero. So, will it ever be possible to go all the way, to reach the holy grail of cold, 0 Kelvin?
Getting to absolute zero is tough. Nobody's actually been there at absolute 0.000000 with an infinite number of zeros. That last little tiny bit of heat becomes harder and harder to get out. And in particular, the timescales for getting it out get longer and longer and longer, the smaller and smaller the amounts of energy involved. So eventually, if you're talking about extracting an amount of energy that's sufficiently small, it would indeed take the age of the universe to do it. Also, you actually need an apparatus the size of the universe to do it, but that's another story.
Absolute zero may be unreachable, but by exploring further and further towards this ultimate destination of cold, the most fundamental secrets of matter have been revealed. If our past was defined by our mastery of heat, perhaps our future lies in the continuing conquest of cold.
Nova is a production of WGBH Boston.